Okay, welcome to this video on what we are calling two-source interference. In other words, interference between two sources of waves. Now, before we start to talk about this in more detail, I just want to start off with a bit of a reminder for some of you, and just some information for some of you, depending on whether or not you do maths. If you do maths, you've probably seen this before, but this is going to be important later on. So just sort of use it almost as a starter to the video. I just want you to imagine that we're looking at some very small angles. Now, if you actually work out sine of a small angle and tan of a small angle, you will find that they are very roughly the same. You'll also find that that number you get is very roughly the same as the actual angle itself, as long as the angle is in radians. So for small angles, the angle theta is approximately equal to sine theta, which is also approximately equal to tan theta, as long as theta is in radians. Okay, so you'll see later why that's relevant, but just wanted to sort of fit it in at the beginning just to remind you. Okay, let's start thinking then about this two-source interference idea. And we're going to start off by just imagining that we've got two sources of waves. So we're going to consider two sources of coherent and monochromatic waves. Right, two words there, then we need to make sure we're happy with the definition of. Now, I did actually mention this one, monochromatic, in the fibre optics video. Monochromatic just means a single wavelength. In the case of light, a single colour, but the ideas that we're talking about, I want to make sure we're being quite general, because these will apply to any waves, not just light. This one, though, coherent. Now, the definition of coherent comes up a lot in exams. The question, what is meant by coherent, comes up very often, and often it can be 2 marks for this. So if you've learnt this definition, easy 2 marks. So if you've got two wave sources which are coherent, first of all, they have the same frequency and therefore the same wavelength. And the second point that's important for coherent sources is that they have a constant phase difference. Now, often that phase difference will be 0. You've got two waves in phase. If you've got two sources in phase, they obviously have a constant phase difference of 0. But it doesn't have to be. The key thing is, though, that that phase difference is remaining constant. Okay, let's sort of look at what we mean by that then. Okay, now I've moved on to graph paper so I can draw this next bit accurately, just to give you an idea of what's going on here. I think the best way to imagine this, to start off with, is to imagine waves on water. You know, if you drop, say, a stone into a pond, you'll see the ripples spreading out from that point. And if you imagine then doing that at regular time intervals, you'd essentially be creating a wave. You then imagine somebody else further along the ponds doing exactly the same thing at exactly the same time. You've got two sources of coherent waves. And we're going to think about what would happen in that case. So let's imagine then, there is one source of waves, and here is another source of waves. And the waves are obviously spreading outwards. Okay, we're imagining almost this is the bank, this is the water. The waves will spread outwards this way. And we're going to look at the wave fronts as they spread forwards. So if we looked at this a small amount of time later, we would see a wave that's spread out. Oops, that's not drawn very well. But a wave that's spread out from the first source. And then similarly, you'd see the same thing over here for the second source. If you then look a little bit later, you'd see another wave. I'm not going to draw this in fully now, but out here, that's again has spread out from this point. So what I'm going to do, I'm going to draw in, I'm going to do it more neatly using a compass. I'm going to draw in the wavefronts, and we'll see what would have happened after a short period of time. Okay, there we go. Not perfect, but you get the idea. Now, remember that the lines that I've drawn here are the wavefronts, so they are representing the peaks of the waves, the crests of the waves. And so you can see there are certain points, for example, straight down the middle here, look, where you've got peak and peak, peak and peak, peak and peak. So we've got the peak of one wave meeting the peak of another wave. Now thinking back to when we talked about interference, you've got crest and crest, or peak and peak. That's going to give you constructive interference. You're going to see what we would call a maximum there because you've got the peaks meeting the peaks. Similarly, there are other points along here where you've got the peak of one wave meeting the trough of another, for example, here. So there, you've got the peak from one wave from here, and you've got the trough from the wave that's coming this way. Now let's start to look at where those lines are. So, constructive interference lines. Well, there's one straight down the middle. Now, that makes sense because if you think about it, down the middle, the distance that the wave has travelled from here and here has got to be exactly the same. So you're going to get peaks meeting peaks. But there's then another line. We look, here are some more points where they cross there. So there's another line that comes down like this, and similarly on this side. Okay, there'll be another line over here, and again over here. Okay, now I'm not drawing this really accurately at the moment, but you can see those blue lines. Those are representing constructive interference. Okay, so those are constructive interference. So actually there are more lines than just that. Those are just examples. Look, I mean, there's another one in here I could have drawn. I will put it in actually just so it's clear. There's all those points where you've got crest and crest. Now, there are similarly, sort of in between those, look, there are going to be areas like here, where we've got crest, crest and trough, straight down this line here. So actually, in the middle there, in the middle there, in the middle there, in the middle here. Okay, I appreciate this is very difficult to see on the camera, but that's showing the destructive interference. Okay, now this setup that we've got, that is going to lead to a series of maxima and minima. So where we've got the constructive interference, that's going to give me a maximum. So that's where we will see a maximum wave, a large amplitude wave. And then the destructive interference will give us a minimum. And in fact, if this is perfect interference, then there's no absorption anywhere and the waves are staying at a constant amplitude, the minimum will be 0. Now in reality you won't quite see 0 because actually, take this point over here, the wave from this source has gone a smaller distance than the wave from this source, meaning probably the wave from here will have a lower amplitude, so they won't cancel completely. But in theory, that minimum will be 0. So this creates a series of maxima and minima. Now let's think about the sort of conditions for the different cases, and this will hopefully make this my terrible diagram here make a bit more sense. So let's first of all think about where we get the maxima. Well, the maxima will occur, and that, by the way, is just the plural of maximum. The maxima occur when the path difference of the waves from these two different sources is an integer number of wavelengths. Okay, let's sort of think about what that means. So take a point on the wave. Let's just take that point there. I'll put the black dot that you can't really see very well, but just here. So from here to here, the path length, as we would call it, from from this wave source to that black dot is 2 wavelengths. 1, 2. The path length from this wave source is 1, 2, 3 wavelengths. Therefore, the path difference is 1 wavelength. Okay, so the path difference is just the difference in distance between the paths of the 2 waves, the paths they have taken to that point. So maxima are going to occur when the path difference is an integer number of wavelengths. So n here is just an integer. So it could be 0, 1, 2, and so on. Okay, so this line down the middle here, that's where the path difference is 0. Next one out, that's where the path difference is 1 wavelength. Next one out, the path difference is 2 wavelengths, and so on. Okay, and remember, path difference just means the difference in distance between the paths of the 2 waves. Now, similarly, the minima, well, let's look at a minimum on here and we'll see. So let's take, I'm going to take that point just there, where I'll put the red dot. And again, I appreciate it's very difficult to see. So from this wave here, we've had 1, 2.5 wavelengths, sorry, from this source, 1, 2.5 wavelengths. The wave from here has travelled 1, 2, 3 wavelengths. So we've got a path difference of half a wavelength. We could take another one. Let's take, I don't know, that point just there. So from this source, we've had 1, 2.5 wavelengths. From this source, we've had 1, 2, 3, 4 wavelengths. So the difference is 1.5 wavelengths. So these are basically occurring when the path difference is half a wavelength, 1.5 wavelengths, 2.5 wavelengths, and so on. Now the way we can write that mathematically, minima occur when the path difference equals, and the way we can write this is n plus a half times lambda. Okay, because this n plus a half, n again is an integer, so n plus a half, that gives me that half, 1.5, 2.5, and so on. Okay, and so we get these points where we get maxima, we get these points where we get minima, depending on the path difference between the 2 waves. Okay, now, having a look at this, now unfortunately you do get strange patterns on the camera. This is much better in real life. But what there is actually on that picture is a single dot in the centre and then a lot of concentric circles around it. So it's almost like our source of a wave. Now what I've got here is an exactly the same version, exactly the same picture, but on acetate. Now if I put that on the first, what you can then see is these strange, funky patterns. Now, what this is showing, okay, don't worry about these edges where strange things have happened, but if we look along these points here, you can see the dark lines, the sort of black lines and the white lines. And the black lines are where we have essentially got maxima. And the white lines are where we've got minima. And so we can see that just by having 2 sources, and if we change the distance between the sources, we can see that we change the pattern. Right, all I've got there, look, is the same picture twice, and we get these funky patterns. Okay, now, instead of sitting here playing with these all day, let's actually look at some real-life applications of this. Now, like I mentioned before, you could see this with water. If we were in school, I'd probably show you the ripple tank, where you've got 2 sources and you can see these patterns a bit like on the screen here, but with water. You can also do this with sound. If you have 2 speakers a certain distance apart, playing the same sound, so playing sound of a fixed frequency, the same frequency for both speakers, and you actually walk along in front of the speakers, you will find the sound gets louder and then quieter. You go through maxima and minima. But the most common application of this is a very, very important experiment, which is called Young's double slit experiment. And that's going to be the topic of the next video.